Hello and welcome to the second half of Phys 1201. This part of the course will deal with oscillations, waves and light, and it will be structured as follows. For the first half of this section we'll deal with oscillations, damped oscillations, waves, light and optics. And this will be an overview, so not too much maths. We'll look at some general properties of waves, and how light can be treated as a wave, and then look at some optical instruments like telescopes, microscopes. So some applications sort of stuff here. For the oscillations and damped oscillations, we'll look at their general properties and some basic maths, but not too much detail. In the second half, we're going to go back to oscillations and do it in a lot more detail and find ways to quantify the quality of an oscillation and talk about how phase and driving and damping all interact with each other to make the behavior of an oscillator actually quite complicated. We'll also deal with coupled oscillations where you may have two or more oscillators that can exchange energy. And this is a really rich area of physics and describes a lot of behavior in the physical universe. And so we'll deal with this in some depth. And from coupled oscillations, if we have many oscillators all coupled together, we can derive a wave equation and look at properties of waves from the point of view of the wave equation. So as you might have guessed, this second part of this section will be in more depth with much more maths. Now you may think this is a bit of a strange structure, but there are some good reasons for doing this way. First and foremost is that this part here with coupled oscillations requires some material that you learn in maths this semester, namely eigenvalues and eigenvectors. So I want to make sure you've covered that before we do the coupled oscillations. So we did that over here directly after the oscillations. You may not have done that yet. And secondly, the research has shown that if you see something more than once, you learn it better. So if we talk about oscillations here and then come back and talk about them again over here, the chances are more of this material will stick. So this is the reason why the course is structured the way it is. So here's an overview of what we'll be doing. We'll be starting with the simplest oscillation, a mass on a spring, bouncing backwards and forwards, and we'll have equations that describe this in terms of the mass and the properties of the spring. Then we'll look at what happens when you add some damping, so the oscillation loses energy over time, like this, and we call this damped oscillation. And from there we're going to start talking about waves and different kinds of waves, for example a transverse wave or a longitudinal wave, like this. So there are different kinds of waves, and we'll talk about which waves exist in which different systems. We'll talk about some properties of waves like the Doppler effect, where the source is moving, for example, so the wavelengths are different depending on which side of the source you're on. We'll talk about the case when it's subsonic and also the case where it's supersonic, like these ducks travelling faster than the wave speed in water. Then we'll start thinking about interference of sources. So here are 2 point sources that are interfering with each other because they're emitting waves, and in some places the waves add up and some places they destructively interfere, so we'll talk about this kind of interference effect. And we'll talk about interference of waves of different frequencies. So the red waves and the blue waves have a different wavelength or a different frequency, and when you add them up, we get patterns like this, and we call this beating. And we'll talk about standing waves, where we take a wave going one direction, a wave going the opposite direction, we add them together, and we get a wave which is stationary and just changes its amplitude from positive to negative. And these standing waves we also call modes. And modes are everywhere in physics. For example, the electron shells we find in atoms. Basically the entire universe is composed of modes, and we'll talk about why this is. Then we'll start talking about light. So this is a model of the plane waves of light, where the red and blue sine waves here represent electric and magnetic fields. And we'll talk about how light works, what a plane wave is, what polarization of light is. And we'll talk about how we see light, how we experience light as humans with our eyes, with lenses and detectors, and how some other creatures experience light, for example the mantis shrimp, which has extraordinary eyes with far more photoreceptors than we have. Then we'll think about the limits of our own vision. So we're trying to see some small object here. How small an object can we see using our retina and the lens in our eye? How much can we improve it by adding lenses in front of our eyes like magnifying glasses and microscopes? And we'll think about telescopes as well and looking at things that are a long way away. And finally we'll look at diffractions. That's waves changing directions. So we've got waves that come in and diffract around objects, so the waves can change direction. And diffraction is really interesting. It's the wave property of light that gives you diffraction, and it limits how well you can make some optical instruments, and we'll talk about that as well. So at this point, we circle back around and start with oscillations again. We'll start talking about damped oscillations, where the damping is very high, and we'll start talking about driven oscillations as well, where rather than just having the energy flowing out of the oscillation, we're actually pumping energy into it. And we'll look at situations where the amount of damping changes and see how this behaves. And we get some very complicated behaviors when we look at driven oscillation in particular. Then we'll look at coupled oscillations. So we'll have two oscillators, and the energy can flow from one to the other and back again. And we can have equations describing many coupled oscillators, and we'll talk about how to derive these equations, using the Euler-Lagrange formalism, no less. Then we can generalize this to many masses, say on a string like this, or springs like this, and this is where waves come from. So we can get transverse waves or longitudinal waves, depending on which picture we take in this case. So then we can look at the properties of waves. So for example, waves can be reflected like this and transmitted, or reflected and transmitted like this. And so we'll find out under what circumstances do we get a pi phase shift here, and what circumstances do we not. And we leave the course then at this point where we have finished thinking about properties of waves, and at least in one dimension. And in second year, we'll go on with this treatment of waves and look at things like dispersion, where waves at different frequencies travel at different speeds, and make the whole thing more complex, more rich, and more exciting again.